We go.
Okay. Welcome everybody to the New England Dynamics and Number Theory seminar. Today's speaker is Minju Lee from Yale University, speaking on orbit closures of unipotent flows for hyperbolic manifolds with Fuchsian ends.
Okay, great. It's actually the first time this semester when the speaker is from New England. So we came back to our own turf for a while.
Okay,
welcome, Minju.
So thank you for coming to my talk, and then thank you organizers for inviting me to this seminar. And I'm going to talk about joint work with Hee Oh, and as Felipe has told us that the title of my talk is Orbit Closures of Unipotent Flows for Hyperbolic Manifolds with Fuchsian ends. And I'm going to present classification results for orbit closures under some assumptions. And this assumption is called hyperbolic manifold with Fuchsian ends. And I will probably spend some time explaining what these objects are. But let me start with the background about the ergodicity. So my G is going to be a connected simple linear Lie group. For example, G can be SNR or the connected component of SON1. And let U be a one parameter subgroup consisting of unipotent elements. This means that the elements small u sub t is going to be was it a question? Okay, I continue. So this U is going to be a one parameter subgroup consisting of unipotent elements, which means that the elements small u sub t is going to be a matrix consisting of matrix whose eigenvalue consists of only one. And gamma is going to be a lattice inside G, and M will be the Haar measure on the quotient space G mod gamma. And recall that a discrete subgroup gamma of G is called lattice when the volume of the quotient space G mod gamma is finite. And by volume, I mean the Haar measure. Then we have the classical theorem of Moore, which says that if we have an unbounded subgroup inside G, then whenever you have a finite volume of G over gamma, then this subgroup will act ergodically on G mod gamma with respect to the Haar measure. So in particular, our one parameter unipotent subgroup is unbounded, so it will act ergodically on the space. Oh, sorry, was there a question? Okay, so I continue. As a consequence of ergodicity, we know that for almost every point, if I take almost every point X and its U orbit closure, it's going to be everything. So this theorem tells us that typical U orbit closure is going to be everything, but it does not give you information about every single U orbit closure. And the following theorem of Ratner tells us what the U orbit closure is for non-generic points. It says that U orbit closures are homogeneous. More precisely, if I take any point X inside G mod gamma and its U orbit closure, then you can find some subgroup, a larger subgroup L containing U, such that the orbit closure XU bar is going to be itself a single orbit of this subgroup L. So XU bar is equal to XL, and this XL is going to be a closed orbit. Before this theorem of Ratner was proved, there were special cases which had been proved previously, for example, by Margulis and also Denis Margulis and Isha. And one remark is that the theorem is true in a greater generality So this theorem will hold if I replace the unipotent subgroup U with any subgroup that is generated by unipotent elements. And the main theorem that I want to present in this talk is an analog of this Ratner's orbit closure theorem in the infinite volume setup. So I need to explain what this infinite volume setup is. And as a first step, I want to explain what a convex cocompact manifold is. So here is some bit of hyperbolic geometry. Previously, G was a simple Lie group, but in the rest of my talk, I will fix my G to be the connected component of SOD1. And it will be useful to interpret this G as an orientation-preserving isometry group of HD, where HD is the unique, simply connected, d-dimensional hyperbolic manifold. And in this picture, I have HD, and I also have this boundary SD minus 1. So it is a fact from hyperbolic geometry that HD has a nice compactification, which is the sphere at infinity, denoted by SD minus 1 in my picture. For example, if D is equal to 2, then H2 as a set will be an upper half space in the Euclidean space R2. And the sphere at infinity is going to be the union of this x-axis, where y coordinate is 0, and I have to add the infinity point. So this R union infinity is going to be a sphere at infinity, and then this compactification behaves nicely with respect to the action. So there is a G action on HD acting by isometry, and this action extends to the boundary sphere. And now gamma is going to be a torsion-free discrete subgroup, and it's no longer a lattice. It could be a discrete subgroup of infinite volume. And I get an associated manifold because gamma is a subgroup of isometry group, and because it is torsion-free, if I mode out by gamma, then HD mode gamma is going to be a hyperbolic manifold, which I will denote by M. And there is a subset denoted by lambda, which is called limit set. And this is a subset of the sphere at infinity. So lambda is going to be some gamma invariant subset, which is closed. And it is in fact a unique gamma minimal subset in SD minus 1, which captures all the non-trivial dynamics of G mod gamma. And associated with this limit set, I consider the convex hull denoted by hull of lambda, and this will be a subset inside HD. And this is a subset of HD, whose compactification contains the limit set, and it's going to be the smallest convex set satisfying this property. And this convex hull is again going to be gamma invariant set. So I can take a quotient out of this, which will be called a convex core of M, and it's going to be a subset of M. So you just, so I have this convex core denoted by core of M, and we will say the hyperbolic manifold M is convex cocompact whenever this convex subset is compact. So that's my definition of convex cocompact. And I want to explain another hypothesis in addition to convex cocompactness, which is having Fuchsian ends. So now I will assume that my manifold M is already convex cocompact. And then gamma is going to be a Zariski dense subgroup inside G. This means that gamma is not contained in any proper algebraic subgroup of G. And we will say that M has Fuchsian ends if the convex core, which was previously defined, this is now by definition a compact manifold with boundary. And if it has a totally geodesic boundary, I will say that M is a convex cocompact manifold which has Fuchsian ends. So this condition, the convex core having a totally geodesic boundary, this condition is what I call when this condition is satisfied, I will call that M has Fuchsian ends. And in this case, I have the following picture. So there is a convex core, which is by definition a compact manifold with boundary in the middle. And then if it has a totally geodesic boundary, so I'm drawing a picture of three-dimensional manifold. In that case, a boundary, if the boundary is totally geodesic, then this is going to be a hyperbolic surface, which has genus 2 and genus 3 in this picture. And the complement of convex core is the union of these blue pieces. And each piece is going to be homeomorphic to surface cross interval. And there might be some more complicated topology going on in the convex core. So this is a picture that I have when I have a convex cocompact manifold M, which has Fuchsian ends. And the name Fuchsian ends comes from the fact that these blue pieces is what we call, more or less what we call a Fuchsian manifold. Actually, you have to consider the hyperbolic double of this, but this is the reason that we call this a Fuchsian end. But now I will give an equivalent characterization of being convex cocompact with Fuchsian ends. Actually, I will assume that M is convex cocompact and then give you an equivalent definition of having Fuchsian ends in terms of the limit set that I have defined several slides ago. So remember, there was a limit set. There was a gamma invariant closed subset, which was actually gamma minimal subset inside my sphere at infinity. So I consider the complement of this limit set inside SD-1. So this is going to be an open set. So I can write this as a union of its connected component, which I will denote by B sub I. And when this B sub I is a round open ball, it's not just a topological ball, but it has to be round ball. And then if their closure are pairwise disjoint, so that Bi bar intersection with Bj bar is empty for all I different from J, then this manifold actually has Fuchsian ends, and it is an equivalent definition. So you can, if you want, you can forget about the previous definitions and then just think of your manifold. You have manifold M, which is associated to your gamma, and associated to your gamma, you have limit set. And just by looking at the complementary region, if it is a union of this Bi, it will have Fuchsian ends. But I'm assuming that M is convex cocompact anyway. Okay, so this is a picture that I have. So this is a picture for D equals 4. And the set is the picture sits inside S3. And this union of blue balls are going to be union of Bi, and the complementary region is supposed to be the limit set. Now I did not draw infinitely many ball Bi's, but there should be infinitely many Bi's, and then they're going to form a dense union of this whole set S3. And to obtain the example for convex cocompact manifold with Fuchsian ends, you can instead look for a compact hyperbolic manifold which has totally geodesic boundary. And in fact, there is a one-to-one correspondence between them. So suppose you have a convex cocompact manifold with Fuchsian ends, then by definition, if you take the convex core, you get a compact hyperbolic manifold, which has totally geodesic boundaries. And conversely, if you start with a compact hyperbolic manifold that has totally geodesic boundary, then there is a canonical procedure of turning it into convex cocompact manifold with Fuchsian ends by attaching these Fuchsian end pieces to each boundary component. So in the previous slide, I had this blue region, which is called a Fuchsian end. I will just attach this boundary times interval to each pieces, and then that you can get a convex cocompact manifold with Fuchsian ends conversely. And one remark is that if d is equal to 2, then everything gets degenerate, and every two-dimensional manifold, which is surface, so every convex cocompact two-dimensional manifold will always have a Fuchsian ends, because everything gets degenerate in this dimension equal to 2. And the main theorem that I want to present was classification results. So I want to present an orbit closure theorem analogous to Ratner, but we use the assumption that the manifold, the associated manifold, the manifold associated with gamma is convex cocompact and has Fuchsian ends. And the reason that we use this assumption is that, first of all, in general, the orbit closures can be pretty wild. And in fact, they can behave as badly as a closure of geodesics in closed surfaces. So unlike the unipotent flow, if you look at the diagonal flow, then their orbit closure can have a non-integral Hausdorff dimension. And it is provided, an example is provided in the paper of McMullen, Mohammadi and Oh, where they give an example of quasi-Fuchsian manifold. And then they have a copy of H2 immersed inside this three-dimensional manifold. And if you take the orbit closure, it will behave almost as badly as this closure of geodesic. In particular, they will have a non-integral Hausdorff dimension. So we don't attempt to give a classification result for a general setup. Now, I try to state the main theorem shortly, but I need one more definition. So let G be SOD1 as before, and gamma be a convex cocompact with a subgroup with Fuchsian ends. This just means that the associated manifold M, which is quotient of HD by gamma, will have a Fuchsian end, and it's going to be a convex cocompact manifold. And I will consider any subgroup H that is connected, any connected closed subgroup H that is generated by unipotent elements inside it. So what are the possibilities for H? In fact, we know what the possibilities are. For example, when G is equal to PSR to C, any such subgroup H will be conjugate to one of these three cases. So it's either PSR to R, or the upper triangle matrix, which has real entry, or upper triangle matrix, which has complex entry. So the second one has dimension 1, and third one has dimension 2. And any such subgroup will be conjugated to one of these three subgroups. And now I can state the main theorem. Under this assumption, if you have G mod gamma, where G is SOD1 and gamma is convex cocompact with Fuchsian ends, and if you take any such H, then their orbit closure is going to be homogeneous in this set RFM, which stands for renormalized frame bundle. I did not define this And I owe you the definition of this set, but this will appear in the next slide. But for now, you can think of it as some compact subset inside G mod gamma, which is invariant under diagonal action. I will give a precise definition in the next slide, but let's just think of it as some compact subset inside G mod gamma. And to state this more precisely, if I take any point X inside this RFM and take the closure XH bar, then you can find a larger subgroup L containing H such that XH bar is going to be itself a single orbit of this subgroup L. So this is going to be XL after intersecting RFM. So the conclusion is that XH bar intersected with RFM is going to be XL intersected with RFM. So remember that in the lattice case, the Ratner's orbit closure theorem says that this was true without taking intersection with any subset. But now in this case, what you can say is that they are relatively homogeneous in this sense. And actually, we can give a explicit description of this orbit closure XH bar, but to do that, I will have to introduce more notations. Oh, and I have to mention that this theorem was previously proven by McMullen and Mohammadi and Oh in their paper for the case when D is equal to 3. And our theorem is going to be a generalization of their result to a higher dimensions. Okay, so I need to explain several subgroups and objects in G mod gamma. So A is going to be a diagonal group, which can be interpreted as geodesic flow, a subgroup corresponding to geodesic flow or frame flow under the sort of identification with G and the frame bundle of HD. And what is RFM? It's going to be a subset of G mod gamma with the following property. So I take the orbit of A orbit of G, then I want that orbit to be bounded. So it doesn't depend on the representative of this G. And it is going to be a compact A invariant subset. So A invariance comes from the definition because it was defined to be A invariant. And the compactness comes from the fact that RFM is going to be fibering over the convex core of M. And by definition of convex cocompactness, this convex core is a compact set. And RFM fibers over a compact set, and then the fiber is going to be also compact set. So this is a compact A invariant subset. And N is going to be a contracting horospherical subgroup corresponding to this group A. So N is a set of elements such that if I conjugate it with a of t and let t goes to minus infinity, then it will converge to identity. Maybe it would be helpful to give an example of the case when G is equal to SO close to 1 or PSL to R. In that case, A is just a diagonal group. You have these 2x2 matrices where you have the entry A, 0, 0, A inverse. And this is what A is. And in that case, the contracting horospherical subgroup is going to be the upper triangle matrix with the real entry. The one-dimensional is upper triangular subgroup. And then I'm going to further introduce group RF plus M and also the semi-group A plus. So let me first explain what A plus is. So A was the full group. A was a group which is isomorphic to R, and I wrote as A equal to little a sub t, where t is in R, and I'm going to choose a positive direction and call this semigroup A plus. So A plus is going to be A sub t, where t is greater than or equal to 0. So you have this semigroup A plus inside A, and R plus M is the set defined as follows. So this is an element G such that the orbit under this semigroup is bounded. So RF plus M is going to be a larger set than RFM. And in fact, it turns out that this is just a translation of RFM by all possible N orbits. So this is going to be a larger set. And it is now A invariant because RFM was A invariant and A normalizes N. And it is also N invariant by definition. And it is no longer going to be compact. But we will need this RFM and R plus M to describe the orbit closure in the next theorem. Okay, here is another notation. So now N was, remember that N was the full contracting horospherical subgroup. Now I will consider a subgroup U inside this N, which could have smaller dimension than N. And for each such group U, I will define a subgroup denoted by H of U. And what is this H of U? This is nothing but just the smallest closed simple Lie group containing A and U. So it's just a notation that might be confusing, but the example, after looking at the example, it will be clear what this group is. For example, if dimension of U is equal to 2, then HU, for example, if the dimension of U is equal to 1, then HU is going to be isomorphic to PSL to R. So you have this SL to R triple, like A and U and the transpose of U, this form a SL to R triple. And the H of U is apparently the smallest closed simple Lie group containing A and U. And similarly, if dimension of U is equal to K, then H of U is going to be isomorphic to the connected component of SO K plus 1, 1. Now here's an example for G equal PSL to C. If U is this one parameter unipotent subgroup, then H of U is just going to be PSL to R. And in fact, when G is equal to SO P1, we know that any closed subgroup generated by unipotent elements is conjugate to either U or H of U for some choice of U inside N. So by this characterization, by the final remark, to describe the orbit closure for subgroup generated by unipotent elements, it suffices to describe the orbit closure for either U or HU. And that's what we have in the following slide. So here's theorem A and theorem B. And theorem A says U orbit closures are relatively homogeneous. So this will give you a classification of U orbit closure, which says if I take any point X inside RF plus M, remember that RF plus M was N invariant, actually AN invariant, subset of G mod gamma, and I'm going to take the U orbit closure. Then I know that the U orbit closure is going to be a subset of RF plus M because RF plus M was already N invariant and hence U invariant, and it is a closed set. And the theorem is saying that XU bar is going to be the intersection of some closed orbit XL and this ambient space RF plus M, where L is a larger subgroup containing U. And similarly, we have H orbit closure classification, and this is also relatively homogeneous, but with a different ambient space. So what this tells us is that if I take any point inside RFM and take HU orbit closure, then it's going to be an intersection of homogeneous space or a closed orbit XL and the ambient space, which is now going to be RF plus M times HU. And in both of the theorem, we know what the candidate of this group L is. For example, in the second theorem, we know that L is of the form, if I take H orbit closure, the group L that appears in the right-hand side is always going to be of the form H of U hat times some compact subgroup C, where U hat is subgroup N that contains U. And now these two theorems gives you an orbit closure classification for U orbit and HU orbit. And because of the final remark in the previous slide, this will give you an orbit closure result, orbit closure classification for any subgroup that is generated by unipotent elements. So remember, there was a remark that in the final remark, we have any closed subgroup generated by unipotent elements is conjugated to either U or HU. And by combining this theorem A and theorem B, the main theorem will follow. So to deduce the main theorem, we need to prove this theorem A, and it will be sufficient to prove this theorem A and theorem B. I will skip this slide. Okay, so to deduce the main theorem, we will have to prove this theorem A and theorem B, and the method is to induct on the codimension of U inside the horosphere subgroup N. Okay, so first, here is an induction hypothesis. I'm going to run an induction, and then for the first hypothesis corresponds to theorem B in the previous slide. It tells you the HU orbit classification for points inside RFM. And the second one corresponds to U orbit classification, U orbit closure classification, which corresponds to theorem A in the previous slide. But to run the induction argument, we had to use another induction hypothesis. So these two were not enough. And here is the third induction hypothesis, which is an analog of a topological analog of equidistribution result. So suppose you have a closed orbit, sequence of closed orbit X sub I, L sub I, where L sub I is an intermediate subgroup between U and G. And we further assume that none of the infinite subsequence of this is going to be contained in a subset of the form Y0L0D. And what is this Y0L0D? First of all, Y0L0 is going to be a proper closed orbit inside G mod gamma, and D is going to be a compact subset sitting inside the normalizer of U. So when these hypotheses are satisfied, then it says the limit supremum of this set XII intersected with RF plus M is going to be RF plus M. So in the lattice case, if you can just remove RF plus M, you can replace RF plus M with G mod gamma, and you will see the corresponding equidistribution type statement. And now I have these three induction hypotheses, and I'm going to run the induction on the codimension of U inside N. So let's say one sub m hold if the previous statement 1 is true for all u which has codimension less than m inside n. And similarly, I will say 2m and 3m hold if the corresponding statement in the previous slide is true for all codimension less than m. And then in fact, some of the base cases are empty statement. So we will start with the base case when m is equal to 0. So saying that saying that u has codimension 0 inside n just means that u is equal to n. And we will see that in the previous slide, the base case for the 1 and 3 is empty, because if u is equal to n, for example, for the first hypothesis, I want to know the HU orbit closure. But if u is equal to n, HU is just the whole group G. So there is nothing going on in the first statement. So this is empty. And similarly for 3, if u is equal to n, then this XILI should already be the whole space G mod gamma. Here is going to be G mod gamma, and then the statement is also empty. So the only non-trivial statement is the hypothesis 2 for the base case, and it actually follows from n minimality of RF plus M, which was proved by Winter. So it says the following. It says RF plus M is n minimal set, which means that if I take any point x inside RF plus M, take the n orbit closure is going to be the whole space. So for 2, the base case is to classify n orbit closure. So x n bar is going to be RF plus M always, which is valid, which makes 2 valid. Okay, so we have the base case for 1, 2, 3. And then here is a diagram that explains how the induction step proceeds. So suppose you have the hypothesis 1, 2, 3m. So we have this second line. Second line is what we know. And now you go to prove 1 sub m plus 1, and then 2 sub m plus 1, and 3 sub m plus 1 in this order. So what this diagram is telling you is that to prove 1 sub m plus 1, you look at the arrows targeting on 1 sub m plus 1, and their source, there are 2 arrows targeting on 1 sub m plus 1, and their source is 2 sub m and 3 sub m. And those 2 are the hypotheses you will need, which you will use to prove 1 sub m plus 1. And similarly, to prove 2 sub m plus 1, you have these 3 arrows targeting on 2 sub m plus 1, and the sources are this 1 sub m plus 1, 2 sub m, 3 sub m. And you can just chase this diagram, and then this explains how the induction proceeds. Okay, so at each induction step, there is a common strategy that we use. There are 2 steps that is commonly used. The first step is to find the closed orbit, and the second step is to enlarge the closed orbit to a bigger closed orbit. More precisely, suppose you want to know what the orbit closure of XHU bar is, and as a first step, you look for a closed orbit which is contained in the orbit closure XHU bar. Now suppose if your orbit closure XHU bar is equal to this closed orbit, then you are done, because this is what you are looking for. And if it is proper subset of the orbit closure, then as a second step, you want to find another closed orbit that is larger than this, and you will you will keep doing this until you arrive that XHU bar is actually some single orbit of some subgroup, a large subgroup L containing U. So that this is a common strategy that applies to each induction step. And there is an important recurrence property that we use. And this is called a thick recurrence property, or a thick return time of unipotent flow to RFM. So this is a property that, this is one reason that we require this convex co-compactness with Fuchsian ends. Now, given the convex co-compact gamma, you can find a positive number k greater than 1, which only depends on the gamma, such that the following holds. So if I take the point x inside RFM, this is an arbitrary point, and you have any one parameter subgroup U sub t inside N, then I can look at the return time t of x. This is a time set of time t such that x U sub t comes back to RFM. And if your manifold is convex co-compact with Fuchsian ends, then this return time is k thick in the following sense. So this is a definition of k thick. We say a subset of R is k thick if for any given positive number, you look at the symmetric interval, which is union of this closed interval, the one being minus kr to minus r, and another one being r to kr. And to say that this set is k thick, for every symmetric interval that you choose, this set has to meet this symmetric interval for every r. And then this property holds for convex co-compact manifold with Fuchsian ends. Oh wait, how many cases? I think I have like 10 minutes. No. Okay.
Between 15 and 30, I think.
15 and 30. Oh, okay, okay. Yeah, I think I was yeah, so I guess, yeah, so now let U sub t be a one parameter unipotent subgroup inside N. And here is the most important ingredient, which is called the avoidance theorem, to which the most of the hard work goes into. So if I have a one parameter unipotent subgroup inside N, then I will consider the following singular set, which is the union of all closed orbits inside G mod gamma under the subgroup, which is connected, closed, and contains the subgroup U sub t. And then the avoidance theorem says the following. I look at the set, which is the intersection of RFM and this singular set. So this is what is written in the left-hand side, the intersection of singular set and RFM. And you can find a compact set, E sub j, exhausting this set, singular set. So I can write this as a union of this compact sets, and it's said such that which satisfies the following property. Now, if I have a compact subset F inside RFM, which does not meet E sub j plus 1. Now I'm fixing some j. Suppose that you have a compact set F inside RFM, and that does not meet E sub j plus 1. Whenever this happens, you can find an open neighborhood O sub j of E sub j, such that for every point x inside F, if you look at the return time to RFM, but return time to RFM minus O sub j. So you want to avoid your unipotent trajectory going close to this set E sub j. So this is the return time that you look for, and then this is going to be a 2K thick set. So that's the avoidance theorem. Yeah, so the reason the difference between the classical avoidance theorem is that the difference between this theorem and the classical avoidance theorem is that the classical theorem tells you that the return time return time to the set which avoids this singular set is going to be is going to have large Lebesgue measure, or in other words, this unipotent trajectory spends small time with respect to Lebesgue measure around near this singular set. But now we want to consider the return time to RFM, and RFM is a fractal set. And if you look at the Lebesgue measure, if you just look at the return time of XUT returning to RFM, this set is already a contour set, and then if you have a Lebesgue measure 0, so you have the previous avoidance theorem does not tell you much about much because the Lebesgue measure, the whole Lebesgue measure is already going to be 0. So we have to establish this kind of theorem, and this is the part where most of the hard work goes into. And in particular, you want to apply this avoidance theorem in the following case. The case you want to apply is the following: if you're given a point xi converging to a generic point, meaning that it's not a singular set, x is not in the singular set, and if you have any sequence ti, which I don't have any control, you're given some sequence ti going to infinity, then you want to find return time small t sub I in this interval t sub I to kti, such that this xi uti converges to a generic point. And actually, this avoidance theorem is not strong enough to give you this, but it gives you something, and this with this result, and combining this result and the third hypothesis about this equidistribution, you will be able to get an orbit closure classification. Okay, so that's the end of the talk. So this is not the end of part 1, but it's just an end, because there was another part in the other talk, but not here. Okay, so thank you for attending.
Why don't we thank our speaker? And are there any questions or comments?
So maybe I have a, maybe it's not a very smart question, but does your proof contain the proof of a proof in the lattice case, or is it just some kind of an induction step?
You mean, does the proof recover the lattice case? Oh, no, our proof recovers the proof of lattice case only for the cocompact case. For the cocompact case, and then there is still some assumption that we are using. So, for example, one property that we use is that it could be possible that the singular set could be empty in the cocompact homogeneous space. Like every like orbit can be every orbit closure can be like dense. You might have no closed orbit inside it, but in our setup we always have a singular set. So that's the one point that we also make use of. And so so the answer to your question is our proof recovers the proof for the cocompact lattice case with some additional assumption. Okay.
Interesting. So what about invariant measures? Anything be said?
Measures we don't know. Measures we don't know. So I guess even in smaller dimension, in dimension 3, the measure classification is probably not known. So maybe one might expect the n invariant ergodic measures. Oh, no, sorry, not n invariant. This which is all. Yeah, so there is a candidate for the ergodic measure, which is called the Berger-Roblang measure, but it is not known at this stage, I guess.
Sorry, not known that it's ergodic, or not known that it's the only one?
It is known that it is ergodic, even for one parameter subgroup. So there's a Berger-Roblang measure, which is an invariant ergodic measure, and then I think Mohammadi will prove that this is also ergodic with respect to any one parameter subgroup, unipotent subgroup. But what is not known is that whether this is the unique measure appearing in this setup.
Okay. Yeah, interesting.
Other questions?
Can you explain a bit about the EJs? Like, how each one is unique, corresponding to an end, or what are those exactly?
So this is so what this EJ is. So you can you can describe this singular set S of U sub t as a union of something called singular tube. So you can think of EJ as something like that. So suppose you have a closed orbit, say, suppose this is SO31. Suppose this is SO31, and then suppose you have a SO21 orbit which is closed. Then you consider some compact subset inside the horosphere group N. Then I can translate this closed orbit XSO plus to 1 by this compact piece. Then this is going to be EJ is going to be set of this form. So if G is SO plus 3, 1, and you have closed orbit, say SO plus 2, 1 closed orbit, then you can multiply some compact part of this horospherical subgroup N. Then if you make this compact set larger and larger, it's going to be exhausting this singular set, and EJ is exactly set of this form.
Other questions or comments?
And
Thank you.
So my question is about the setting. So you're dealing with convex, cocompact, hyperbolic manifolds with Fuchsian ends. And I like this characterization you gave, where you said that this is the same as looking at groups, where the complement of the limit set in the boundary was the union of round open balls, right?
Yes.
So my question is why do you need round? Like, why can't you do a more larger class? See, my real question is, I was thinking about geometrically finite groups in general. And so where do you need this roundness? Like, why can't they be topological balls that are disjoint?
Yeah. So in fact, in dimension 3, when d is equal to 3, there is a result for which relaxes this condition that this ball is round. It could be a topological ball, as you mentioned.
So they have the same relative homogeneity kind of result, you're saying?
Yeah, more or less. They have a classification result for those orbits which intersects. They have some restrictive condition, but more or less they give a satisfactory classification where the complementary of limit set is not necessarily round open balls, but a topological ball. And then, so the one difference is that if you have a round open ball, then you get this recurrence property that I was mentioning at the last part. So this thick recurrence property. So this thick recurrence property is obtained quite easily if you have round balls. And if it's not a round ball, then this is the hard part of the second paper of McMullen and Mohammadi and Oh, where they deal with these topological balls instead of round balls. And then, but in the higher dimension, we make use of this recurrence property for every direction, and then it is crucial that we have this for every direction. And also what is known is that for those when the case where this is not a round ball but a topological ball, they're actually quasi-conformal conjugate to this convex cocompact manifold with Fuchsian ends. So it is known in 3 dimensions. They are there is
right.
So they can be deformed into the case.
But that's very special, right? Because there you have a Teichmuller theory in low dimensions. In higher dimensions, you don't have such a nice, deformation theory.
Right. Yes, definitely.
It's really interesting, though. So, I mean, do you believe that you can, in future work that you can get rid of it, or is it really it's more of a technical abstraction? The way I'm listening to you, that's the idea I'm getting, right? So it's something that maybe you could remove in the future. This is just a relaxed seminar, so don't just feel free to say.
Okay, so the answer is I really don't know, because a lot of things breaks in higher dimension, and then I probably have enough intuition for that. So yeah.
It's that's completely. It's really interesting what you have as it is. So I was just, thanks.
Okay, thank you.
Okay, so if there are no further questions, maybe I can start by stopping the recording, and then we can talk for a while, some more if you want. Anyway, thanks, Minju, for a great talk.
Thank you.
And see you guys every Monday for the rest of the semester.